Hello everyone, my name is Tofunmi Sodimu and I'm a student in Dr. Ding's Imaging Lab. The project I am presenting on is the live sheet imaging of the structure of the neonatal mouse heart. Heart failure affects thousands of Americans each year, and the neonatal mouse model has been used to study cardiac injury and repair. However, the mechanism behind this process is still unclear. Therefore, we propose the use of a light sheet fluorescence microscope to study this process. Light sheet fluorescence microscopy, or LSFM, is an imaging technique which involves the use of a thin plane of light to illuminate a transparent sample from the side. The fluorescence emitted by the sample is captured by a detection arm that is located orthogonal to the illumination arm. LSFM is known for its high spatial resolution and minimal risk of phototoxicity and photobleaching to the sample. This makes its use advantageous in the study of the neonatal mouse heart. In figure 1, we see a schematic illustration of our light sheets. The omega naught denotes the waist of the light sheet and it determines the extra resolution of our system. In figure 2, we see a flowchart of the steps taken to eventually record our images. In figure 3, we see the description of the resolutions of our system determined by measuring the point squared function of fluorescent beads under the same conditions as our sample or postnatal day 1 mouse in this case. The lateral resolution along the XY dimension is 2 microns, the axial resolution along the YZ dimension is 10 microns, and the axial resolution along the XZ dimension is 9 microns. For this project, we built a single illumination, single channel LSFM system. Single illumination because the sample is illuminated from one direction, that is, we have one illumination arm, and single channel because we have one detection arm. At the intersection of these two arms, we have the chamber with the heart mounted in a glass tube within it. In figure B shows a close-up of the detection lens, illumination lens, and the chamber, while figure C shows a close-up on the chamber with the heart mounted in a glass tube. We use agarose to mount the heart in place, while refractive index matching solution, or REMS, is used to match the refractive index of the heart with the glass tube and the cover glass. Glycerol is also used to match the refractive index of the glass tube and heart and ultimately ensure that the laser doesn't refract during imaging. And in figure D, we see the actual image of our illumination arm with the 3 laser lines and their different propagation paths. And in figure E, we see the actual image of our detection arm with the stage, camera, filter wheel, and chamber. The system is controlled by a LabVIEW control algorithm. The logic behind the algorithm is that as the stage moves the sample along the Z direction, the camera captures along the Z direction is along the detection axis. The camera continuously captures successive images while the laser keeps propagating. This enables us to obtain an image stack which can then be reconstructed into a 3D image of the heart. And figure B shows the LabVIEW front panel. To obtain the imaging results for this project, we employed the clarity clearing technique. The purpose of this technique is to reduce the lipid and water content in the heart using detergents and replacing it with an aqueous solution which roughly matches the refractive index of the remaining contents of the heart. At day 7 of applying this clarity protocol, we see that the heart is more transparent than it was at day 0. Figure B shows different slices of the heart captured at different imaging depths by our LSFM system, while figure C shows the 3D reconstruction of our hearts from this image stack rather. And in summary, our LSFM system is capable of imaging the neonatal mouse heart with a high spatiotemporal resolution. This system represents the first LSFM system at CTD, and it can be optimized for the study of more advanced processes like cardiac regeneration. Thus, we plan to incorporate multi-view image acquisition to improve the isotropic resolution of our system, remote focusing to improve the axial resolution of our system, and we plan to employ the IDISCO clearing protocol to obtain more transparent samples or hearts. Thank you for listening to my presentation.